last time. We stopped at aggregation. Administrative, there's not a lot to talk about today. The one thing to note is that you can take a look at your exams if you want after like 15 minutes of this lecture in my office. If you want to see them, if you want to see my evaluation, just come talk to me after this. Okay, so let's go quickly through. We talked about filtering and aggregation. I'm going to skip filtering because it's rather straightforward. Just a quick recap of aggregation. So the idea of aggregation is that we represent a group of elements by a smaller number of derived elements. And so we have talked about item aggregation as, for example, in histogram, and there we said that for the number of bins is sometimes a little bit tricky to predict. So you could make that interactive to do that. So we had this nice effect here where we could see a pattern that in the different bin size was 20 bins, that we couldn't see was 10 bins. Then we talked about density plots, box plots, which are also known as box and whisker plots. One thing that I didn't mention here maybe was that this like quartile 1 minus 1.5 times the interquartile range and so on. This is it's a convention, but it's not strictly observed. So if you plot a box plot, you should always mention what the whiskers mean. Sometimes people plot other values for the whiskers and for the box at the center. This is a figure that I found that I didn't show last time. So I think this is pretty interesting. Like you can see, this is similar to Anscombe's quartet. You have in Anscombe's quartet we have 4 statistical values that show exactly the same, or that actually have exactly the same values, but they're derived from completely different data. So in this case here we have 4 different distributions, and they actually produce all the same box plot. So this just shows you that the box plots are not, like, they're a good indicator under the assumption that you have something like a normal distribution. But if you have something like a peak distribution, a bimodal distribution, or a skewed distribution, it might not be the best choice. We went through that. So here's a comparison of box plots versus bar charts. And box plots aren't great, but you shouldn't use bar chart with error bars for distributions, and you should also not use them for showing an average plus a standard error. Violent plots are an alternative to box plots. They essentially show you more about the distribution, so you can see something like the bimodal distribution here. And then we talked about binning. So instead of drawing all of these points individually, we have these binned heat maps where we simply assign an intensity value or increase the intensity value every time we count a point in one of those bins. I'll talk more about these hierarchical parallel coordinates. We continue talking about spatial aggregation, which is kind of a problem, like if I want to aggregate over an area, how do I choose the unit? So we talked about, like, this would be a grid layout, and these could be, well, they all look like Voronoi diagrams, but not necessarily are Voronoi diagrams in this case, because there's not a central point. Then we talked about gerrymandering, that's kind of the real life effect of that. And then Voronoi diagrams, which simply give you the essentially the area that is closest to a specific point. And so you can use them both for visualization directly, for example, like color coding, or for user interface features, as we saw here in the map. Okay, so then we continued with clustering. And clustering, really, I can stress this enough, is really a very important technique in visualization. So we distinguish between partitional algorithms, which simply divide a data set into a set number of clusters, hierarchical algorithms, which produce a similarity tree, where you can dynamically cut a dendrogram to produce the number of clusters. Then we have biclustering, where we cluster dimensions and records at the same time to have a globally optimal solution. And then we had fuzzy clustering, which we didn't talk too much in detail about, but here we have probabilistic cluster assignment. So an element might be 80% in this cluster and 20% in another cluster. We will talk about clustering for ordering in the context of tables today, for pixel-based techniques. And you can, of course, also use them to aggregate. So here is an example that I'll have in the next slide deck too, about the clustered heat map. So this is a pretty efficient display of data. You can draw a lot of points and you can still see patterns. But of course you can't see individual values here too clearly. And the comparison to the parallel coordinates, which are essentially useless for this case. Okay, let me skip over this. I'll just skip over that. So the message here was really about if you use clustering, you have to be sure that the clustering algorithm fits to your data. So here are examples of data sets that don't really work well with k-means clustering, because k-means has the assumption that the clusters have roughly equal size and that they're roughly circular. So in this case, it's clear that we have like an outer ring and an inner center, but k-means actually partitions it into two circles. The same here, so this would be something where you might guess that k-means does a decent job, but in fact it does not, because the size of the cluster is quite a bit different. So, and then we talked about dimensionality reduction, especially first we started with principal component analysis. And principal component analysis is really the idea of taking a high dimensional space and finding the essentially axis through that space that preserves most of the variance. So instead of, and if I only take the first principal component here, instead of saving for every point an x and a y value, I could just save the distance from this point here, both positive if it goes to the right, negative if it goes to the left. So I essentially, with a single number for every single data point, I can capture like a large amount of the information that is contained in this data set. So I would just lose the variance that is along the second principal component. And this was the nice example, and I'm just going to reopen this because this is really a very illustrative example here. The 3D versus 2D. So here I have a 2D plot that I can turn around, and the question here is, what is the perfect projection for this to show you as much variance as possible in 2D? And you can do this with principal component analysis. So you can see here we have principal component 1, which is not surprisingly along the long structure of this data set, and principal component 2 is in this direction. So that is a 3D example that illustrates this nicely, but of course it really works also for larger dimensional data sets, as you can see here. So we have the 17-dimensional data set where we have attributes of England, Northern Ireland, Scotland, and Wales, about how they, what kind of food they consume. And if you do a principal component analysis, you will see that Wales, England, and Scotland is clustering around one area, and Northern Ireland is quite different from them. That's something that you have, is probably more difficult to see in this bar chart. So you can see here is a difference in terms of fresh potatoes. Okay, so this is where we stopped last time. I just wanted to show you one example of how principal component analysis was used in a student project a while ago. So this is a little bit tricky to explain. I'll try my best. This is a biology problem. So what we have here is a protein sequence, and what we had as input data was we had 500 or 300 different protein sequences, and we had a classification of which of these proteins actually produce something like a functional protein. So these are every single cell here on the x-axis is one amino acid, and so we had 200 sequences or 300 sequences with different amino acids. So what we then try to do is we try to understand the properties of these amino acids. So amino acids, they have special properties. For example, hydrophobicity is my favorite example. Either an amino acid attracts water or repels water. And so if you substitute, in a functioning protein, if you substitute the critical amino acid that is very hydrophobe with one that is very hydrophile, you have the hypothesis that this might actually affect the function potentially. So the idea was to simply, there's a lot of these indices, and we simply classified them into these main categories. So we calculated a set of a couple of hundred amino acid indices, and then we classified this them into these 6 bins. And for all of these 6 bins, we calculated the principal component for every single amino acid. So essentially what we did, we got an average score for each of these indices according to these parameters. And then we plotted here, like for every single amino acid, a bar that showed us how much the principal component deviates from the natural protein, from what you would find, what we call the reference protein. And the theory was then that you have a functional breakdown whenever you have these very high peaks. So here, the idea was that in here, in this area, so this is a focus and context technique, here you have the amino acid sequence, and here you have the details about that. So here we have the stacked bars to show us the deviation from the principal component of the amino acids. And here you could switch between stacked and aligned, depending on what you want to show. And so what is also important for these amino acids is, or for these proteins, is of course their physical shape. So we did, this is a WebGL renderer of the protein structure, and it highlights, like it's simply connected with the brush here. So whenever I drag the brush, you can see what the corresponding area in this 3D protein is. And the arcs up here show you the distance. So there's a threshold here, and you have between 5 and 10 angstrom. We show you these ribbons so that you can see co-located structures. And if I were to extend the brush, you can see that the ribbons get updated. So this was a 2-man student project. It was pretty impressive, but they also were very motivated and submitted it to a bio visualization contest. They didn't win, unfortunately.
So what won?
Okay, so multidimensional scaling is similar to principal component analysis in its effect. The big difference is that it doesn't use the data by itself, but it uses a similarity matrix. And based on the similarity matrix, these points are laid out. So essentially what you can do is you can define your similarity matrix in a custom way, and then you can lay it out in a custom way. So MDS is really just like an umbrella term for ways of taking a similarity matrix of items and then laying them out in 2-dimensional space, for example, or in whatever dimensional space you want to. So here you can see this one example that we had in one of the design critiques by Mari and Dirk, where we had these, in this case, philosophers, or we also had musicians and so on. So in this case, we had similarity scores of how similar are they to each other, and that's how it's laid out. And this is really popular for text analysis, but it's also popular for other data sets. One of the big problems with all of these dimensionality reduction methods is, however, that we have to take something very high dimensional and reduce it to 2 dimensions. And necessarily there's going to be an error. So there's 2 problems with that. So first, we can't really interpret what is the meaning of X, what is the meaning of Y. They actually don't really have a meaning. They really, what we only see is the things cluster together, and we can infer about similarity. But even that can be wrong, can simply be an artifact of the dimensionality reduction. So here we have this example this is the Stanford dissertation browser. And so they classified various fields based on text analysis and tried to understand which areas have kind of the same vocabulary. And here you can see that petroleum engineering seems a little bit more similar to neurobiology, medicine and biology than, for example, to civil engineering or mechanical engineering. And that is something that isn't very intuitive. So you would expect that the engineering fields somehow cluster together. And in fact, it turns out this is really just an artifact of the dimensionality reduction. So what they did to show that is to use interaction. So whenever you would click on petrol or in any of those fields, you would get a rescaling so that you could actually get accurate distances from the selected point. So you could see, okay, if I actually select petroleum engineering, I can see that it is indeed pretty close to all of the other engineering fields, and that this proximity to neurobiology and so on was really just an artifact of the dimensionality reduction. So this, last week at VIS, there was a very cool project presented, which is called Probing Projections, and I would encourage you to take a look at it yourself. So if you go to this URL down here, oops. To this URL, come on. To this URL, you can play around with it. Maybe take 2 minutes and try to explore the technique, what it does, whether you think it's useful or not. Let's do that for 3 minutes and then I'll talk about it. So there's the prototype. That's where you actually have the technique.
Back to the URL.
Yep.
The prototype doesn't stick when you mouse off dimension.
The what?
So when you hover over a dimension, you get your gradation, but when you go off of it, it doesn't stay. There's no way to keep that and go pointing.
Yeah. I think if you click on it, yeah, if you click on it, it seems to work.
Clicked on it and it still doesn't stay. Oh well, it's a prototype.
Okay, so I really like this technique because it actually combines, and it actually fixes multidimensional scaling, because my biggest critique of multidimensional scaling is, of course, that we can't really trace it back to the raw data, and we have these artifacts of dimensionality reduction, and they actually fix both problems. So what you can see here, if you hover over a single point, you can see every single raw measure, right, and where this point in particular belongs. And you also have this list here, and so if you hover over these lists of these attributes, you can see the areas that essentially are that drive the points, like if you have a high life satisfaction, you're driven to the dark corner. And if you have a low life satisfaction, you're driven to the upper corner. And so these maps, they are kind of like, they give you an idea of what the meaning of these variables could be. Of course, it's fuzzy, like it is not really clear. So you can see educational attainment seems to be in the lower edge, and you can see life satisfaction seems to be in the lower right corner. But we can actually see the individual values for each of those. Like when we hover over here, we can see not only the actual numerical values here, but we can also see where it is in the distribution for the selected point. Another super nice feature is this correct distance button here. So when I click here, it actually shows me the actual distances exactly from what we saw in this Stanford dissertation browser. So this is Italy, and now I've clicked it, I can see that France moved from this position down here to that. So now what we can do is we can make accurate judgments of similarity of the selected item to all of the others. So, but it means also that, for example, the relationship, the similarity between Austria and New Zealand is something that I can't trust anymore at this point. So I really can only trust the relationship of Italy to all of the others. And then it has a couple of very nice other features. Especially I like the two things, this displaying the dendrogram. So here we have the dendrogram. Do you have a question?
What do you mean by corrected distance? How do we calculate?
The corrected distance? So when I click this correct distance point here, like what I have right now is, and it's tricky to actually get into this. What I have right now is like a compromise to show you the similarities globally between all of the points. Right, and so since I'm trying to have multiple objectives here, like show the similarity between all of the points, I can't really show it faithfully for every point. So it's like a best guess. These are clusters and so on. But if I want to pick a single point, I can actually show the true similarity from this single point, and that's what I'm doing here. So here I have the globally, like the global compromise of similarities, and if I click on correct distances here, I don't care anymore about how Finland and Denmark relate to each other. I only care about how Finland relates to Italy and how Denmark relates to Italy. So that essentially, like if you focus on a single element, you can actually correct for that, and that's a very, very neat thing to do in a dimensionality reduction technique. And this dendrogram also goes a little bit into this. Like you remember when we talked about clustering, the dendrogram essentially did tell us how similar are 2 points, and then we could do these dynamic cuts. So here we can see the dendrogram, and of course it's laid out in space, so it's not as nice as if we had just like a regular tree layout, but it's still a tree. So we can see, for example, well, it's a little hard to trace, but Austria is pretty closely related to Switzerland and Canada, United States and Israel, because they're kind of at the same branch in terms, same branch of the dendrogram. And so since we have a dendrogram here, we can also dynamically define clusters. So this is really the great thing about hierarchical clustering algorithms, that we can dynamically cut this dendrogram, and that's exactly what they're doing here. So I can rapidly redefine the number of clusters. And then I can actually interact with these clusters and I get an average technique, report of the elements in this cluster. So this is really a paper. Nothing in there is new, but they brought everything really nicely together and they created something very useful. And this is actually a bachelor's thesis. So the bachelor student did this as his project and then wrote a paper. Okay. Another really interesting technique that we saw last week in Chicago is also with multidimensional scaling for temporal data. So they call it time curves, and the idea here is that you take time points, for example, weather data, and instead of just like showing them in a linear fashion, you're actually more interested maybe in how similar is today's day very similar to today's weather very similar to the weather 3 weeks ago, and it probably isn't since it's snowing for the first time. So we would have an outlier. So what they do is they take those time points and do a multidimensional projections of the attributes, and then reintroduce the time aspect through drawing a curve through it. So what you have here is essentially, like here you start, let's say in January, and then you go through here and you can see all of these days are very similar, and then we have here the weather is suddenly changing a bit. And so then like we continue and so on, and then could be the summer. Like I'm making the data up here, right? So this is not really what happened here. And then we could go back essentially over winter, and that's when the year essentially completes. So we have again a similar weather. And they really did a really great job in also explaining how it works. And this is interactive, so you can essentially like influence how strongly the projection is done here. And so there's many examples, there's a lot of explanation. You can actually create them yourself. And here are a couple of examples from many different data sets. So they have like one of the nice examples is state of Wikipedia articles, and you can see edit words, for example. Like if somebody changes an article and adds a section, it's a very different state. But if there's an edit word going on and one person is changing it to state A and another person is changing it to state B, you see those two clusters and lines going across those clusters. Yeah, so take a look at this website if you find this interesting. I really like the technique. Okay, so that completes the lecture on dimensionality reduction. Next is tables. Okay, so this is a little bit weird that we're talking about tables only that late in the class, but a little bit, well, part of it was that we kind of wanted to give you the knowledge about volume rendering before the homework, so like this would come a little bit earlier in the course. When we talk about tables, think back to when we classified the data types, and this is a figure from the book. So now, like today we're talking about tables, and the next time I'm actually giving a lecture myself, we'll be talking about networks and trees. Then Aaron will continue talking about fields, but today it's about tables. And so for tables, there's this interesting classification of how you lay it out, and really how to essentially choose your spatial position is really important. So we have these 4 different categories. We have to express a value directly, to separate, order, and align regions by keys, then by the choice of your axis orientation, and that's where we come into parallel coordinates and so on. And so here is parallel coordinates, and here we have the heat maps and so on. And then we have these dense layouts, which you probably haven't heard about yet. And so for tables, really the spatial channels are the most effective and the most important. So how you choose your space, as always, is really critical. And this is also like for the reasons of perceptual efficiency, of course, but also we are really good as humans to kind of orient ourselves in space. So we know, like, if you're sitting on your desk and you put like you pile up, let's say, your classes in different areas of your desk. If you come back the next day, you will remember this is the visualization pile, this is the machine learning pile, and so on, simply by spatial orientation. So like spatial, how you partition space and so on, that's really very, very important. Just a reminder, we have in a table, we have items and attributes, and so when we arrange tabular data, some of the attributes are chosen to be keys or values. And what it means specifically, you'll see in a second. One thing that I want to disclaim here is that the scale of the tables makes a big difference on the approach that you can choose. So the rest of this lecture will be structured by how you partition and how you lay them out, but what you really, in many cases, drives the choice of which technique to use is the scale of the table. So you need different approaches for normal and high dimensional tables. So for example, if you have about 50 dimensions, you will find visualization techniques that just work. And if you have about 1,000 items, they also will work. So 50 by 1,000 These are rough guidelines, but if you have a table like this, you don't have to worry about it. You can simply show every point on the screen, and it will be okay. If you have more than, if you have about 50 dimensions and about 1,000 elements, yeah. But if you have more than 50, or if you have like many dimensions, for example, 1,000 dimensions, you need these analytical methods that we just talked about, like dimensionality reduction, principal component analysis, and so on. So this is simply not tractable with just regular visualization techniques. And the same is true, like if you have records, if you have only about 1,000 records, you can just use visualization. If you have a lot more than 10,000 records, depending on your visualization technique, but typically you will also need to do some aggregation, some filtering, and so on. And another aspect that we didn't talk about yet is homogeneity. So the techniques you choose and how scalable they are depends a lot on the homogeneity of the data. So what do I mean by homogeneity? So here are two tables. One of them is homogeneous, the other one is not. So here we have Bob, Alice, and Chris, and then we have attributes about them, age, gender, and height. And so these are different data types. So we have an inhomogeneous table. So numerical, categorical, numerical, and also on different scales. So we have to essentially, for every single one of those dimensions we have, or each of these attributes, we have to also visualize the axis. But if we have something like this, Bob, Alice, and Chris, and they're all in let's say running labs. You can see they start with beats per minute, like heartbeats per minute at 65. And then in the second lap they're at 120, and then the third lap they're at 145. This is homogeneous data, so all of the tables are on the same scale, and so I can do a much more compact representation with that. And so this essentially kind of also gives you the space of the techniques that you could use. So if you have not a lot of data, you don't need analytics, but if you have a lot of data, you need analytics. And so this is essentially here the space of kind of the most important tabular visualization techniques according to their analytical components. So parallel coordinates and scatter plot matrices, you can do them completely without any intelligence. You can just plot them. You can make them better with clustering methods or with ordering methods, but it's not necessary. Pixel-based visualizations, which are very scalable, they need some kind of smart ordering, otherwise they're useless, so they're kind of in between. And then we have these very strong analytical components like multidimensional scaling. Okay, so back to this like fundamental classification. The first type of how you could lay out a table is by simply expressing the values and not using keys at all. So the example here is scatter plots. And that's a very, like we've seen this a lot. We have here is life expectancy versus infant mortality, and you can see that there's a linear relationship. But this is a very simple chart, and this only, of course, in this case works for 2 dimensions, and they show their variation. We don't have to partition space based on a key, we simply plot the data. So if we want to encode one key attribute, we actually arrive at bar charts. So here we have, these would be the keys. The dimensions are used as keys here in this case. So different animals, and then we see the average weight of these animals. And here, of course, the line chart is similar to that. So again, very simple idea, and I'm not going to spend too much time on it today. So what happens if we want to encode multiple keys as attributes? We come into the space here of matrices, volumes, and recursive subdivision. So matrices, we'll talk about them later, but first let's talk about bar charts. And so here we have 2 keys. Like this is a Titanic data set, how many people died and survived, partitioned by class. So you can see first class, second class, third class. And so what we have here is we have 2 keys. We have the first key is the class, and the second class key is whether they died and survived. And we're showing this as a bar chart. And this also illustrates the difference between a proportional bar chart and an actual bar chart. And you can see, like, okay, there's a lot of people that died in first class, but in terms of fraction, only about, let's say 35% of the passengers in first class died, whereas about 70% of the passengers in third class died. So this is again the difference between a regular bar chart and the proportional bar chart. So here is a chart that I think we've talked about this, but I just wanted to add the figure here because I think it really nicely illustrates the different options that you have if you want to do multiple keys with bar charts. So for reference, there's the pie chart, so here you have the stacked bar chart, and then you have small multiples essentially, and what is called the layered bar chart and the group bar chart. And all of these, they have really, like as I mentioned before, there's good reasons to use all of these, but it depends on your task. So here you can easily compare within a class, here you can easily compare between the classes for a specific time point. So here is a stacked area chart, and so just as a comparison to the 100% stacked area chart, in this case here we can see the overall, let's say, values pretty nicely, but in this case here we can see the proportions are much better. And so if we compare all of them, here is a comparison of a stacked, like a proportional area chart in terms of market share versus a line graph. And so one of the things that is a little bit tricky here is to see what is really going on. So if you plot the same thing here as line chart, it's pretty evident. What you would probably have thought here is that the green chart is actually decreasing in value, but if you look at the line chart, it's actually slightly increasing. And that's the problem of, like, we perceptually don't connect these 2 points here, but we connect these points here, and we've talked about this before. And yeah, so that's a challenge with stacked area charts. And here's a comparison between stacked bar chart, stacked line chart, stacked area chart, and stacked line charts. And as you can see, this is actually, here in this case, we have, this is a weapons data set. How many weapons are sold? There's revolvers, shotguns in blue, pistols in orange, rifles in blue. So you can see that this over time, and it's pretty clear that the overall sale of weapon was higher in 2009 and 2010, but the proportions aren't that easy to see in any of those two charts. Here they are, of course, nice, easy to see, but we lose the overall sum of the sales. So yeah, depending on your task, you have to pick. Okay, so this was the boring part of the lecture, the charts that we talked about quite a bit already, but I thought it was still important to frame this in the context of table visualization. Now we'll be talking about matrices or visualizing data directly as tables. And so one of the most influential InfoVis papers probably of all times is this table lens. This is from '94, and I have one of those nostalgic videos here.
In an information-rich world, the problem is not so much acquiring information, the problem is more making sense of large amounts of it. In our user interface research group at Xerox PARC, we've been exploring the use of information visualization to produce new kinds of documents and new user interface paradigms that allow people to deal with much larger amounts of information than previously possible. Recently, Ron and I turned to the problem of dealing with large tables.
For example, this is a table of the 1986 baseball statistics with 323 rows of players and 23 columns of data. We can put the data into a spreadsheet, but even using a 21-inch workstation display, the data requires 9 full-screen vertical scrolls and 2 horizontal scrolls, making it hard to work with. It's hard to find players or see interesting patterns. In short, it's hard to make sense of the information. We've devised a new way of visualizing and interacting with large tables called the table lens, which exploits graphical representations to compress the information onto the display. In this column, at bats, we integrate a familiar bar chart representation directly into the textual view of a table. Some of the rows, those in focus, show underlying textual values along with the graphical bars. Other rows, those in the context, show only graphical representations, thus requiring less space. By displaying the entire table graphically, with only some of it in focus, this 324 row by 24 column table can be shown using a portion of the screen. The table lens displays 30 to 100 times as much information as a spreadsheet in the same space. With a small set of manipulation operations, the table lens allows fluid navigation and exploration of the data. The focus area can be manipulated using control points and/or keyboard commands. The number of cells in the focal area can be increased or decreased. The focal area can be moved to different rows or columns. Since the essential geometry of the table is preserved, multiple focal areas can be created. To facilitate browsing of context cell values, a mouse feedback area at the bottom of the window shows column, row, and value information. The graphical representations make it easy to spot trends and patterns and to isolate outliers or unusual cases. For example, sorting a column can reveal relationships to other columns. Here, sorting career at-bats reveals correlations in several nearby columns. Notice that career hits is strongly correlated or proportional to at-bats. In other words, most players have similar batting averages. Some players stick out from the curve, two well-known batting stars, Wade Boggs and Don Mattingly. To confirm these observations, we divide career hits by career at-bats, creating a new column, career average. The batting average curve is reasonably flat, as the correlation of the curve suggested, though increasingly noisy with decreasing career at-bats. Furthermore, the length of the bar shows that Boggs and Mattingly have the highest two career averages. If we focus on the salary column, we see that Boggs and Mattingly are paid relatively well for their top-flight batting performances, both of which actually have two teams.
So here we're looking at category.
Nearby, two other category columns, division and league, have become more orderly, indicating a relationship to team, or in database speak, a functional dependency. Since the noisy areas align with the Chicago...
So I guess you got the gist of it. So this is really a neat technique, and this is, especially if you consider that this was done in '94, very remarkable. Yeah, it's still like a lot of papers take inspiration from that. So there's another technique that is also direct representation, and in this case it's more about presentation. How can we create like these kind of tables dynamically? So this is more of an authoring interface to create these Jacques Partin matrices that you could, for example, show in a newspaper, and they have a pretty nice tool. Just gonna show you the video, I think.
Green columns. When she moves her mouse on top of any tool icon, a tooltip appears at the top of the page to recall its function. Tools are organized in groups. Clara first expands the MISC group and clicks on the H icon adjacent to the first row to mark it as a header row. She does the same for the left column. Then she expands the Shapes group in order to turn numeric values into shapes. She clicks on the circle icon next to the first row of the table in order to turn its values into black circles and squares. She is satisfied, so she presses the same icon on the next row and drags down until the last row. This instantly turns all table cells into circles and squares. Now Clara wants a more compact table. Each row can be resized independently using the slider placed next to it. Moving the slider to the right increases row height, while moving it to the left decreases it. She sets all rows to their minimum size by pressing on the topmost slider, drags down until the last row, then drags left to modify all selected sliders. She does the same for columns. She also zooms in using the provided functionality of the browser. Now she wants to tidy up the table. She drags over all black arrow icons, which immediately rearranges columns by visual similarity, which moves similar countries next to each other. She does the same for clause. Now indicators that are similar are close to each other. To better see similarities, she removes the grid by setting all white separators and black separators to the minimum value. Clara continues to format the table to exhibit more patterns and convey a clearer message. This includes inverting the values overall, importance of a good pay, to better show its correlation with another one, the household income. She also emphasizes two rows of a specific type by changing their visual encoding, increasing their height and dragging them aside. She encodes women's suffrage year using lines, and household income using a bar chart. She can choose to reorder only a subset of the rows or to reorder all rows. Now she can already see country groups, with Czech Republic in between, that she moves away. Finally, Clara adds separators and annotations to emphasize groups.
Yeah, so I really like the way how you can, this is of course not an analysis technique, but really just more of how do I format the table to communicate it, but it's really very well done, and I really like the interaction. Okay, I think like you've seen this before. This is the ranking technique, so where we have actually multiple attributes, and we stack them and change them and so on. But I've shown this before, so I'm going to skip over this and continue with pixel-based displays. So pixel-based displays or matrices. Here, each cell is a pixel. And you encode the data in color, using color or values. And as I already mentioned a couple of times, really the ordering is critical for interpretation. So here is an unordered matrix, and if we actually order it, for example by clustering, it actually makes a lot of sense, whereas this here, we don't really see patterns. And so here's a comparison of the same data in a heat map. We have two clusters, the cluster A and cluster, or let's say the upper cluster and the lower cluster, pink and blue. And then here we have parallel coordinates to show you the same data. So for me personally, I think I understand, well, I think people understand both of them actually pretty well, but the conclusions that you might draw from these two representations may be a little bit different. So here you can see the outliers maybe a little bit more clearly. And of course, this is more compact. This shows you the compactness that I've shown you before. And so one thing that is important to know that heat maps are really mainly usable for homogeneous data. So same scale and same type of data. And that's why they, for example, are very often used for gene expression data, where you have like a large matrix of very homogeneous data. I just wanted to throw in an example that I like a lot here. This is about the 3D bar chart, so a 3D problem of occlusion perspective, and I think I've shown this before, but it's really tough to see a pattern here, but if you show it as a heat map, the pattern is very clear. So here is a heat map that is actually published in a Nature paper, and this one is actually not very good, because it encodes a lot of different data types that are not homogeneous with similar values. So here you have gene expression, then you have mutation using the same color scale, and then you have copy number variation, again using the same color scale. So this is a little bit confusing in this case, because if you don't really read the legend very closely, you would assume that those columns kind of relate to each other. This is how you shouldn't use a heat map, really. And then we talked about red-green blindness quite a bit, but here is an interesting example. So here in this one cluster, this is what a person with red-green blindness would see. So here you can see there's a red row and a red column here intermixed with green. But here in this example of what a red-green blind person would see, there is actually no difference. So he would just see these values are high. He wouldn't be able to distinguish between high and low in this case. In comparison to that, the red-blue color map, in this case here, you can see that very clearly, like somebody with red-green blindness can clearly see the difference in this case, so this is a much better color mapping. And one thing to note is also that color is relative. We talked about this in the perception lecture, but if you look at those two cells here with the stars, you would probably say this one here is lower than that one. But in fact, they're identical. And that is because of the context. So here is a lot of dark elements around it, and here are very bright elements around it, and that's what makes you think that those elements are not the same, which when in fact they are. So here you can see two elements that are the same, and this one is perceived as being darker, two elements that are different, but they're perceived as being the same. Yeah, so I've shown this before in the earlier lecture. Here we have the clustered heat map with about 1 million values, and in comparison to that, the parallel coordinates. One thing that you could also do, of course, if you have temporal data, is to show multiple line charts. And so this is a smart implementation in D3 of that, which is called Cubism.js. So you have this horizon charts where the top of a line chart or an area chart is actually clipped and reattached from the bottom. So this mountain here is actually would peak out up here, but it actually has been studied and shown that this is pretty effective, and people actually recognize that pretty well. And then you can create these matrices, these larger matrices of that, and that is also a way of showing, like, if you have a lot of temporal data, for example, stock trading data or so, you could do something like you see here. So what I also like a lot about this technique here is this dynamic crosshair, which is very neat. This is a detail on demand feature, like essentially a tooltip, but it is very smart because it allows you to connect between multiple charts. So if you want to combine various techniques, this is a figure out of one of my papers. You can do that, and you have to be a little bit careful. So what we do here is we show, in this case, multiple different data types. So we have, what is it? This is mutation data. Do people have? No, this is copy number variation data. But anyways, that's not important. So these elements here are of the same data type. And so what we do here, we show them in bar charts, like positive and negative, but we can also aggregate them as histograms or as box plots in that case. And up here we show gender as a heat map essentially. And again, we can aggregate them as histograms. Then we show a numerical variable as bar charts, and we show you the race of these people again as a heat map. And I think by using this structure that labels directly on top of here, and by changing the representation depending on the data type, this works pretty well in contrast to the heat map example that we've seen before. And of course, in all of these displays, it's very important to be able to sort. So here, this is sorted by this particular gene, and then you can try to explore the correlations between the sorted row and all the others. Okay, so I have a design critique for you guys. We will be talking about the three-dimensional, let's say, area surface chart. And so here's the document. I'll hand it out in a second, and here's the website if you want to go straight to the website. It's interactive, so you should play around with it.
Should be playing ocean noises. Oh, I have too many G's. That's my problem. Well, let's go to the document and then maybe click on it.
So there are.
Are you getting, can you get to the document?
M-I-S-Y,
Oh,
M-L-S-Y. Yeah, just anyway.
Oh, M-I.
It's M-I, M capital I-S-Y.
This is down in D3.
Probably not. I would say this is WebGL, but check.
And then it shows 1%.
I don't see anything that says D3.
Yeah. I think it wouldn't be a good fit because D3 doesn't do the 3D very well.
This is really smooth.
Oh, you can send it.
It's got the Google fly-through. It's pretty cool.
You can just between your not using like a small line. Like, for example, if you are to do, isn't it, if it's lower down here, it's bigger. Yeah. What if you just
So it's really like X, Y, backwards. Because 2006. But it's impossible. Looks cool.
If right now you were to buy the low of sushi, if you're willing to buy
You don't know the real value, you can compare because even the dollar here, you can read it because the access is not. I think they just kind of like switch it to this side. The other is switch. Sometimes have some kind of branch across the bridge.
As you drag it, the axis labels spin around too. So they're always facing you.
This one should be the lowest one.
What is the coloration? Isn't the coloration?
Dots. Yeah.
Red means negative. So that means that you go to the best.
And that's funny. There's the one tiny little blip.
Okay, so what's the data that we see in this visualization? What are the 3 dimensions?
Interest rate,
Sorry?
interest rate, loan duration, and date.
Interest rate, loan duration, and date, exactly. So we have interest rate as the z-axis, time on the, let's call it x-axis, and the duration of the loan on the y-axis. So what are the marks and channels that are used here, specifically channels?
Color,
Color, yes.
position.
Yeah, and so do they encode different things, color and position?
They overlap in one of the dimensions.
Yeah, so they actually encode the same thing. So color is exactly correlated to the height of the chart. So you can see that the higher parts of the chart. This is interesting about Mac, that as soon, like, if you quickly react, it takes longer than to boot from scratch. So the higher peaks are also actually darker. So what do you think about the 3D here? Like, I'm always bitching about 3D. What do you think about this here?
It works. Used. Like it might be useful in order to give you an idea of where you might want to look for a better. You know, the fact that you can go and maybe look at a different angle and go away from 3D. I think that sort of makes up for that, and it gives you a way to maybe say, okay, I want to look at this. I'm curious about this, and then go
Yeah.
back to that.
Well, like in previous visualizations, the 3D was used to make it more interesting, whereas in this case it's actually important. It's encoding 3 different actual relevant values, so it's being used appropriately, I guess.
Yeah.
And the fact that you can rotate it allows you to overcome issues with perception of thinking things are smaller or something in the back.
Yeah.
It provides wayfinding. You can actually look at it like a landmark, and
Yeah, so it actually looks like a landscape. And I think that is why this actually works here. Like, did you have a comment?
Oh, yeah, just because it's a landscape, you can be sure like nothing is obscured if you rotate.
Yes, exactly. That's why I think this works, is because we have a continuous data essentially. We have a hull, and there is not a lot of things that are occluded except for the peaks. Like if I look at it like this, it's a little tougher to see into the valley. But from this view, I can probably see like 90% of the values or more. Yeah, I think the 3D is pretty effective here, and so like not every 3D InfoVis chart is bad. This one is actually very good. And if we compare it to this, well, yeah, if you compare it to that one here, this is really tough to interpret. So here we have essentially the same thing projected into 2D in one direction, and then the other one projected. This would be kind of like if I were to do this chart, and if they gave me this data and I only think about it for 5 minutes, this would probably what I would have come up with. Because it's simply like you have 2 spatial dimensions, and then you need another visual variable, and use color. But this is clearly not as effective in communicating what was going on as the other chart. So you can see it if you look at it, but it's not by far not as clear. And now, yeah, so this is the tricky part.
now they're making money.
Navigation. Yeah, but I have a comment on that. So, but it's by far not as clear as this chart here. So, a couple of you guys mentioned interactivity. Any other comments on interactivity? So, one thing that they do really well here, and that's very tricky usually if you do 3-dimensional stuff, is navigation. So it's important, and as soon as you like turn around it like this, it's great, but as you've seen, I simply got lost I didn't know how to get back into it. And so what they do well here is they have these steppers. And the steppers, they essentially take over the camera for you and move you to the perspective where you can actually see what you want. So I really think this was well done. And those are any comments on the storytelling aspect? So you can see whenever I click any of the buttons, it moves the camera around to highlight what is going on, but it also adds annotations. So like here we can see essentially somebody has thought about what is going on and has given us some context. So here we kind of lose the temporal aspect, but in this case they annotate this temporal aspect for us, so it's easy to understand what is going on. And then they kind of zoom in, and I guess here Congress threatens to let the country default, and suddenly the interest rate spiked. But if you compare it to the spikes that were around in 2008, it's very low. Yeah, and then I also like the handling of negative values. So here we have a redundant encoding of negative values with the red color and the space, because it might be pretty tricky to see those values go into the negative area. But the color rate here is probably not on the same scale as the blue one. It wouldn't be as red in that case, which is a good choice. So it's a non-continuous color map, which is again chosen well. So any opinions? Do you like the visualization? Or maybe giving my opinion too much. Yeah, so I think it's well done, and I think it's a good example of 3D. I haven't seen many, but this one is. Okay, so let's take the last 10 minutes to talk a bit about parallel coordinates and similar stuff. I will probably not finish the lecture content, but let's keep going. Okay, so in terms of axis orientation, we have the choice between a rectilinear, parallel, and radial. So here's the fundamental two techniques, the same data set shown as a scatterplot matrix where we have perpendicular axis, and here in this case we have parallel coordinates with parallel axis. And so here we also have this recursive nesting. So in contrast to the original scatterplot example where we had only a single scatterplot, here we do this recursive nesting by the keys. So we have math, physics, dance, drama, and so on, and that's the same thing as we have in the axis here. So let's take a look at scatterplot matrices first. So scatterplot matrix, and I think we've seen them, but let's talk a bit more formal about it, is a matrix of the size d times d, where d is the size of dimension, the number of dimensions, and each row and each column is 1 dimension, and each cell plots a scatterplot of 2 dimensions. So here's this example with this flower data set where we have 3 different species of flower in colors, and we plot sepal width, sepal length, petal width against each other. And you can see that a couple of clusters emerge, but the 2 of them are actually pretty similar. So scatterplot matrices, they're very efficient. Like you can, if you go through them and if you pay attention, they can tell you a lot, and they are very accurate representation, and you can see all of the patterns that are in the data set. But they have limited scalability. So you're essentially stuck after roughly 20 dimensions, because then suddenly you have these big matrices and it's really hard to go through all of them. And in terms of records, you can probably do about 500 to 1,000 records without having to resort to things like binning or aggregation. And so brushing is really important to see any relationships. So we've seen these examples with these brushable scatterplot matrices, and this is very often combined with a focused scatterplot. So you have this matrix that gives you an idea of what is roughly going on, and then you can pick a single one of them and you see them in detail. So what could you do to make them more interesting? So of course clustering and aggregation, for example for color codings, as you can see clusters that you can code clusters. Maybe you have to choose dimensions if you have too many, or maybe you have to choose, you can optimize the ordering, that you can say, okay, these dimensions, they correlate, so let's just put them up in this one cluster. And so that's how you could use algorithmic support to make scatterplot matrices better. I've shown you this example of this linking and brushing, so I'm not going to show it to you again, because we just had it last time for this Plum aggregation. And I think I've shown this before, but it's been a while, so just give you a quick overview of the
The keyboard or the navigation bar can be used.
So what we have here is this scatterplot matrix overview, and then we have the focus view, where they dynamically transition between the individual plots.
For stepping one position in the matrix at a time. Movement is performed as an animated 3D transition from one scatter plot to another, where one dimension remains constant. The user can also scratch the current position in the matrix to see the animated transition from one dimension to the next. To move directly from one part of the scatterplot matrix to another, it is also possible to perform a hyperjump. If the user wants to see the intervening positions, the path planning interaction transitions automatically from one position to another. Finally, path drawing allows the user to draw the path to traverse on the surface of the scatterplot matrix. Scatterdice allows the user to build queries using the query layer box and a lasso tool, and then see how the queries distribute in other plots. The user can move an eccentric label lens on the plot to see the nominal names of the data points. This also works with query selections. Finally, the rows and columns of the matrix can be reordered, either manually using drag and drop.
Okay, so this is a pretty nice system. I haven't seen again many implementations of it, especially if the 3D transitions, probably because it's not super easy to do, and how useful the 3D transitions is actually a little bit doubtful. But I think the way how they handle focus and context here between a small matrix and the big focus plot, and how they handle brushing and so on, is really well done. Okay, so the next major technique when we talk about spatial axis orientation are parallel coordinates. So here, like we've talked about this, and I've shown many examples, but here the axes represent the attributes or the dimensions, and lines connecting the axes represent the items. So instead of having this x and y, we have x and y in parallel to each other. And so the corresponding plot to this scatter plot will actually look like this. And you have to learn how to read this for the first time, but once you actually understand it, it's not a bad technique. So each axis represents a dimension, so line connecting the axis represents the records. And the nice thing about it is that it's suitable for all tabular data types, including categories. So here we have ordinal data in terms of the year that the car was built, and here we have ordinal data in terms of cylinders, and that works. And so all of these values here are of different type. So in contrast to heat map, we can have very different types and connect them to each other. So that's why they're nice. And so I've played with this again before in class, but the important aspect is of course also the filtering here and the brushing. And I think you can also do axis reordering. Well, not in this one. But there's another one that can do axis reordering. Yeah, so we talked about the scalability for many dimensions, so it's not as good as heat maps in terms of scalability. And also in terms of scalability to many items. So this was actually the first piece of InfoVis code that I wrote myself back in 2006. And you can see, well, it's a parallel coordinates plot, but there is no pattern in there, so there's nothing to see. What you could do is you can use transparency. This is random data, so you see what you would expect. And if you use transparency, you can suddenly see patterns. You can do bundling, clustering, but what we also can do is sampling. So and we haven't talked about sampling before, so I'll talk briefly about this in a second. So one of the big limitations of parallel coordinates, and I mentioned it before, is that we only can see correlations between adjacent axes. So like it's hard for us to judge what is the relationship of miles per gallon to weight in this plot. And so you can do that by either brushing or by axis reordering. Oh, there was a video. So when I drag around the axis, I can actually find a better solution, and I can see what goes on there. And what you can also do is you can run an analysis of similarity between the dimensions, and then you can find an automatic, a good ordering, so that you can see it's only, let's say, small changes between axes, and you get these global patterns. So there's papers on how to automatically order dimensions in parallel coordinates and so on. Another issue that we probably haven't talked about is the ambiguity that you have with parallel coordinates. So let's assume you have a line coming in, that this is the axis, and the line exiting, and they intersect here. You don't know, is this line A or line B? Is this line A or line B? This is something that is simply unclear. And so in this example here, we don't know any of the lines here. So this could be anything, and there is no hint for that. So how we could fix this is by using essentially a Gestalt principle of good continuation. So we could draw these curves as splines. In this case, it would be clear what is what. Interestingly, people don't do that. And I think the practical reason is that the other way to fix this problem here is brushing, and you really are more interested in the global trends, and this is really, well, it also has disadvantages because like here we don't see the precise locations and so on, so it gets a little bit more cluttered. So like an analysis of parallel coordinates, it's really about primarily about relationships between adjacent matrices. It has limited scalability, 550 dimensions, and let's say 1,000 to maybe 5,000 records. Transparency of lines can fix that. Picking the right transparency for your data set is tricky, so there is algorithms now for that. Actually, there was one published last year, but typically users take a slider and adjust the transparency. Interaction is really crucial, axis ordering, brushing, and filtering. And as I mentioned, you can make them a lot better with algorithmic support by choosing dimension, by choosing the order, and clustering and aggregating records. So here's an example that I gave you last time briefly, but now I'll introduce it in a little bit more detail. This what is called hierarchical parallel coordinates. So the idea was like parallel coordinates work well for this kind of data, but not so well for this kind of data. So the idea here is really to use clustering, hierarchical clustering, to scale up parallel coordinates. So, and the fundamental idea is that you represent the cluster as its centroid, plus you shade the extent of the cluster with these shaded ribbons here. So now you have an idea of like what is the cluster and what is the variability within these clusters. And then, as this is a hierarchical clustering algorithm, I mentioned that last time, you can essentially drill down and choose the number of clusters you want. So you have this one cluster solution here, you have, let's say, 2 major clusters here, and then you have more of them here, and so on, and then you're back at the mess in the end. So this is a way, and so I think this is a very interesting approach, and I think it's very valuable to essentially show the cluster centroids and the deviation. I think the shading here sometimes is a little bit tricky and it gets a little bit difficult to read. Maybe it might make sense in some situations just to show the cluster centroids. One last word on parallel coordinates. They're probably a little bit overused about people who get into InfoVis. So everybody thinks, oh, this is the cool new technique that I haven't heard before. But they have like a couple of issues, and there's a lot of parallel coordinates haters out there. I kind of like them. I don't use them a lot. I prefer to find other solutions. Another plot is the star plot that is essentially similar to parallel coordinates, but just uses a radial layout of the axis. And I think I'll talk more about this next time. So next time for me will be in probably 3 weeks. So next week is Aaron again, and then we have the project feedback, and then I will be back in 3 weeks. So if you want to look at your exam, come to my office in 10 minutes, and I'll be happy to discuss it with you.
Thank you.